In this lesson, we're going to introduce the topic of electric potential. Here are your objectives. Now first, let's just remind ourselves that when we talked about electric field, we defined the electric field as the force per unit charge. It was a kind of per capita force. And we're going to now do the same thing with electric potential energy to get electric potential. So if we think about electric potential energy as analogous to gravitational potential energy, remember that gravitational potential energy is energy that's stored by virtue of the location of an object in a gravitational field. So here's the ground, and here's a mass. Let's say that's a 1 kilogram mass. And by doing work against the force of gravity, I've stored potential energy in this mass. And if I were to let this mass go, it would be released as kinetic energy as the mass accelerated towards the ground. Also remember from doing problems like roller coaster problems, etc., that we always need to specify a reference. We are measuring potential energy relative to other places, and we decide where the zero is, and we usually make that zero the ground. Now, in terms of electric potential energy, we can do the same kind of thing. Let's imagine a parallel plate capacitor set up like this. Here's the negative, and I'm going to put the positive plate at the top. And similarly, if I take a positive charge from down here, and I do work on it to move it up to closer to the positive plate, that work is stored as potential energy, electric potential energy, in the arrangement of this charge within the electric field. And if I were to let the charge go, it would accelerate downwards as that was released as kinetic energy. Now, once again, just like we had to specify a reference in the gravitational situation, we have to specify a reference in the electric situation. And sometimes, just like in the gravitational setup, we use the ground or a conductor that's connected to the ground or the earth being a repository of charge, or we'll see that we also sometimes use an infinite distance away as being the zero for electric potential energy. But keep in mind this analogy to height. Now, that's electric potential energy. Let's talk about electric potential. The terms are very similar, so we just have to be careful to keep them straight. Electric potential is the per capita electric potential energy. Just like with the electric field, we took the force and divided by the amount of charge. When we take the electric potential energy and divide by the charge, we get this new quantity called the electric potential. And this new idea of electric potential is going to be really useful when we talk about circuits. So remember again that the electric field was defined as the electric force per unit charge. And because the electric force is a vector, the electric field was a vector as well. Again, we saw that the electric field is equal to the force per unit charge. Now we're introducing the concept of electric potential, and it's equal to the electric potential energy per unit charge in the same kind of way. Now, because potential energy is a scalar, electric potential is a scalar as well. And if you look back at this formula, we know that the units of energy in the SI system are joules, and the units of charge are coulombs. So the units of electric potential need to be joules per coulomb, but that has a special name, and we call that a volt. So 1 volt, which has the symbol capital V, is equal to 1 joule per coulomb. It's an amount of energy per unit charge. To get an intuitive sense of electric potential, it's really helpful to think of it as being analogous to height. So in the gravitational situation, if this is the ground, and I were to take a 1 kilogram mass and lift it to a given height, and a 2 kilogram mass and lift it to the same height, the 2 kilogram mass has more gravitational potential energy, but it's at the same height. In the same way, and here I'll draw a parallel plate capacitor system because that's the clearest analogy to the height situation. If I were to take a 1 coulomb positive charge and put it up close here to the positive plate, or a 2 coulomb charge, the 2 coulomb charge, because it's being repelled more by the positive plate and attracted more by the negative plate, has a greater electric potential energy, but it's got the same potential. It's got the same electric potential energy per unit charge. It has twice as much electric potential energy, but it also has twice as much charge, and so has the same potential energy per unit charge, in other words, the same potential. Now, if we think again to our height situation, remember we've always specified a reference point for height, and really we've only been interested in differences in height. When you say that something is at a height of 5 meters, you always are implying it's 5 meters above something else, whether that's the ground or some other reference point. And similarly, for electric potential energy, we're always going to specify a reference potential, and then we're going to be able to measure differences in potential, which we call potential difference, or abbreviate as PD, or also call voltage. And we're going to measure those relative to the place that we set as zero potential energy, zero potential. So the formula that we get is delta V, the change in potential, the potential difference, also called the voltage, is equal to the change in potential energy per unit charge. And because the work that you're doing against the electric force is stored as potential energy, that's equivalent to the work that you've done per unit charge. Let's take a look at an example. If you take a 2 coulomb charge and you move it through a potential difference of 10 volts, and remember 10 volts means 10 joules per coulomb, then by rearranging this formula, you can see that the change in potential energy is equal to Q times delta V, which in this case is equal to 2 coulombs multiplied by the 10 joules per coulomb, or 10 volts, that it has moved through, and so that gives us an energy change of 20 joules. Now, we haven't specified which way it's moving relative to the potential difference, so we could be storing 20 joules of potential energy in it, or we could be releasing 20 joules of potential energy to kinetic energy, for example, if we were just letting it go. But either way, moving through a potential difference of 10 volts implies, for a 2 coulomb charge, a 20 joule energy change. Now, potential is defined by the potential energy of a positive charge. So a positive charge, let's take a large positive charge here and move a smaller positive charge closer and closer to it. So this I'll call situation 1 over here and situation 2 over here. Situation 1 has a lower electric potential energy and therefore a lower potential energy per charge, or lower potential. Whereas situation 2 has a higher potential, or the location at position 2 is a higher potential location. So potential is defined by the potential energy that a positive charge would have. And therefore, positive charges move from locations with high potential to locations with low potential spontaneously. So if I were to let this charge go, it would move from this higher potential location to the lower potential location, from 2 to 1. The locations themselves are defined with potential. So if I put a negative charge here, it doesn't change this from being a high potential spot. It's still a high potential spot. Doesn't matter whether I've put the negative charge, a negative charge, or a positive charge there. But negative charges are going to move from locations with lower potential, like this, to locations with higher potential. Negative charges would move in the opposite direction. Okay, so that's an introduction to electric potential.